Hello everyone. Here I'm Yao. I'm going to talk about the story about the Noril'sk. Sorry. Here is the Siberian LP and LIP, and we can see there is from the three stages and 11 formations. And in these regions, there is three huge Ni-Cu-PGE deposit and hosted in the intrusions named as the Noril'sk 1, Talnakh, and Noril'sk. And all of these intrusions, their replacement is occurred in the sedimentary basins below this flood basalt. And also we can see that the Noril'sk 1 just cut some part of the bottom of the flood basalt. And then we can see that this is the new paleomagnetic date of these regions. And firstly, we can see that the SLRP occurred with a limited number of volcanic pores and individual eruptions. This means the flood basalt is not always occurred along over its whole life. Another thing is that the overbearing intrusions occurred at the same times with the boundary here, with the boundary between the MR and the MK formations. This maybe suggests that they are maybe the parent magmas. Another thing is the light of the work. We can see that from the trace element, the ND formation cells the crystal accumulations, and at the same time, the duplications of the nickel, copper, and the PGEs also suggest that the sulfur segregations occurred in the ND formations. So what's the possible parent magmas? It may be the TK formation below this ND formation, because the TK has the high MG number and it's a picrite basalt. But maybe ND may be also the possible, because the sulfide segregations occurred in the ND formations. And also the MR to MK is also possible because they are the same emplacement. And this is Tony's model for this deposit. Tony suggests that firstly in the magma chambers, the middle magma chambers, the TK magma will do some crustaceans and accumulations, and then drive some sulfide segregations. And this magma takes some sulfide, go into this cell and deck network. And then in the cells, the magma will leave some sulfide in the cells and then go to the surface to form the ND formations. And finally, there is the new replacement of the MR to MK magma into this system. And this magma will have a large interaction with the sulfide here, and then give the high R factors of and the high PGE content of these orbitals. And if Tony's model is right, we can see that the Noril'sk 1 and the Talnakh and the Noril'sk intrusions can be considered as the conduit of this SLRP. But there is something missing problem. One of these is that because if we see the major element, there is no overlap between these intrusions and the flood basalt. And truthfully and replace suggest found some magmatic hydrite in these intrusions, and this suggests that the in-field accumulation of hydrite in the sedimentary during the emplacement is very important for the formation of this deposit. But there is still some things missing. One is that because the melting temperature of the hydrite is higher than the liquid temperature of basalt. This means that the basalt, the ND, MR, MK cannot directly melt those hydrite in sedimentary. And the second is that so the dissolution of hydrite where the sulfur diffusion may be important, but this process is take a long time to occur. And another thing we can see that if we see the Noril'sk 1 intrusions, there is no anhydrite, the green one, there is no anhydrite beside this Noril'sk 1 intrusions, but these intrusions still have the higher isotope, sulfur isotope. Another thing is that the Tony suggests the system is an open system. So the western of the Noril'sk, the intrusions should be connected to the surface and to the float basalt. But the new recent draw call section suggests that the western part of the Noril'sk intrusions is blind cells. So Nadia suggests it's a closed system. So we can see that for this large deposit, there are still many things, many different viewpoints about the parent magmas, about the open or closed system, and also about the in-situ accumulation or the accumulation in the magma chambers. In the following, I will give a new model for this deposit. Firstly, I collect the composition of the CPX thinning crust in the float basalt and calculate their equilibrium pressure and temperature, and all of the data focus on these regions. This may suggest that the CPX will stay in this part, in this magma chamber. And this magma chamber is sit on the boundary. You can see a boundary between the basement and between the top sedimentary. Also, we can see that some CPX also from some CPX in the MR to MK basalt also can come from the deeper magma chambers. This result is also matched by the systematic work. We can see that there is also suggests a magma chamber between this basement and between the top sedimentary. And then I collect all of the basalt the condition and use the alpha MELS to modeling the magma evolutions of this in the magma chambers. Firstly, I take the TK picrite as the parent magmas, and then the country rock, we take the basement. This computation is from the Noril'sk in the cross-east eruptions at the same time in these regions. And then I take 3 different models to model the magma evolutions. All of them have given the similar result, and they suggest that the firstly is to do some crustaceans. 13 is the crustaceans, the magma will realize some heat and increase the temperature of the country rock, and then do some accumulations. The accumulation degree is maybe 20 to 25% of the accumulation can match the evolution, the distribution of the ND basalt. But we can also see that from the MR to MK basalt, they are separate from these magma evolutions. So they also maybe suggest that they come from a deeper magma chambers. And we also can see the trace element of the ND formations can be matched by our modeling for the accumulation in the magma chambers. And then we can see that after the 5% of accumulation in the magma chamber, the sulfide segregation occurred. And we calculated the composition of the sulfur of the nickel-copper ratios, and that's 1.98. And we can see this range of the nickel-copper ratios is matched the nickel-copper ratios in the orbit days. And another thing is that we also modeled the PGEs in the float basalt. It can match very well. And secondly, we can see that because we think the magma chamber is sit on the boundary between the basement and the sedimentary, so we can see that the sulfide and the sulfide in the sedimentary above this magma chamber, they also have the high sulfur isotope. So I calculated that just maybe need 0.4% of hydride in this system will increase the sulfur isotope to the high values of the orbits. Here we can see that there is difference because the TK picrite have a high temperature, so it can directly melting this hydride. Secondly, because this is the magma chamber, so it can take a long time to do this accumulation and to do the homogeneous of the isotope. So we can say the intrusions. The Tony suggests the most interesting things of these intrusions is that like the intrusions looks like the cells or layered intrusions. Here I take one draw call from the Talnakh intrusions. And there is 2 boundaries. One is interfigure boundary and one is sub-boundary. And below this sub-boundary, we can see that is the dismitted sulfide and the massive sulfide. Also below is the sub-boundary, we can see the increase of the oxygen isotope. And we also see this equilibrium of the strontium and the vanadium between the whole rock and between the silicate minerals. And also it's tactic gabbardorite. It means there's many journalists of the country rock and many olive and fused by the phoenix crest. So we suggest that it's true that there is some in-situ accumulation in this picrite gabbardorite series. And above this sub-boundary, there is constant of isotope. And we suggest it's the gabbardorite series. And at the top, it may be the residual series. Another thing we also mentioned is that the sulfur isotope here and the copper isotope from the dismitted to the massive sulfide, there is no sudden change of this isotope. This means that there is no sudden change of the oxygen fugacity, which is in turn means there is not large contribution from the hydride 13, these in-situ accumulations. I also modeling the composition of these rocks. And firstly, we just focus on gabbronorite of series, and we take the parent magma is MR2MK basalt, and we just take 99% of MR2MK and plus maybe 1% of the Olivan finny crust, and doing the crustaceans, and we can see that it's very nice. It matched very well, and the residual melts from these crustaceans, and doing the further crustaceans can match the residual series. And the most important thing is the peak rate gabbronorite series. We can see that here, because there are many linearlists and many Olivan and feldspar finny crust. So I think the parent magma is the 91% of MR2MK and 8% of Olivan and 1% of feldspar. And then doing the 10 to 13% of the in-situ assimilation. 13 is assimilation, we don't include the hydride. And then we can see that the cumulative of the 67% of solid and 33% of liquid have matched the major element of the intrusion. So the trace element is also matched very well for the picturite, gabbronorite. So we can see that, in my opinion, I think there is two stages of assimilations in this story. The first is assimilation in the magma chamber in the deep, and then 13 is the emplacement, and there is some in-situ assimilations here. But both the assimilations can drive the sulfur segregations. But also the most important stage to produce enough sulfide to form the oxides. From here, I think that's firstly, because the intrusion is split and there's not many magma to do in the interactions. And secondly, we think there's little contribution from hydride because the isotope. So we think the most important thing is the sulfur segregation in the magma chamber. And there's another question is how it requires the upward transport of the sulfide. And because the hosting MR-MK magma is sulfur unsaturated, so 13 is the transport. There's some part of the dissolution of the sulfide, and this dissolution will drive the sulfide up gradients. And this is a model for the two stages of the sulfur compositions. The first stage is black lines. It means the sulfur segregation during the assimilation in the magma chambers. And then after the sulfide transport, these dashed lines represent the sulfur upper gradients where the dissolution 13 is transport upward. Another question is how many sulfur can be upward transport? In my opinion, I think the most important thing is the magma overpressure rather than the magma density. Because if the magma still has a large enough overpressure, the magma can still break up the country rock at the top, and then the dike maybe still continue its transport upward. So I I calculated the volume of the MR-MK flood basalt from all the Russian papers, and then their replacement into the magma chamber will drive the maybe 22 MPa of the magma overpressure. And I just calculate the transport upward, the change of the magma overpressure. We can see that besides the 8% of Olivan and 1% of the feldspar, this magma can still carry less than 10% of sulfide. This 10% of sulfide can also form the old deposit. Another thing is that at the low dip of the conduit, there is some formation of the bubble, and the bubble will touch on the sulfide droplet to form the compound drop. The following speaker will talk about this. And finally, we will focus on the horizontal transport of the cells. Because this intrusions in placement into the sedimentary basins. The sedimentary basins is suitable for the deflections and the horizontal flows of the deck. So we can see the maybe 7 kilometers transport of the carrier lag. Secondly, because it's the sedimentary basins, so we can see that it's easily to form the static cells from different magma pores. It may be, so we should also see the sealed, the layered lack of intrusions in the Noril'sk. Another thing, because the emplacement is very low, it's maybe less than 2 kilometers, and the sediment still have some water, fluid, bubble, and in the porosity. And during this emplacement, the heat from the magma will release of this bubble, this fluid, and this may be easier to form the compound drop. And another thing is because it's heat, and the sediment will behave as like the fluid. It's due to the fluidizations. Because there is the transport of two fluid, and we can see that the magma can easily replacement the space of the sedimentary like this. So this is another problem why the Noril'sk can replace along this along this formation of the sedimentary along the flow. And finally, because this is a flow dynamic, I try to understand how the how the deposition of the sulfide in this fluid dynamic. I do the fluid dynamic moldings for this Talnakh. We can see that this one is the dike will totally change to the seal, and this is the deposit of sulfide here. And this is, we see this, the dike is also still the conduit, and the seal is just some part of this conduit. And we can see the deposition of the sulfide droplet. Just go on. We can, this is the this is the Noril'sk. Still two models for this fluid dynamic of the sulfide droplet, and we can see that it can depositions in this part. And we can see these two models may be similarly in the result of the deposition of the sulfide droplet. And finally, I changed to make the comparison between these two models. And the first model, the dike will totally change to the cells, and the magma sulfide will always deposit in the low position of this system. And another thing that we think, oh, this is conduit, and this cell is some part of this conduit. But we can see that if the dike is the conduit, we can see some part of the sulfide will go along this dike and go to the surface floor basalt. But in the floor basalt, we cannot observe the many sulfide droplet. So we think this may be not suitable. And another thing is there is no sulfide in the tips of the intrusions. But here it has some sulfide here. This is also matched the investigation in the field investigation of the intrusions. So we think that in this system, there is two stages of the assimilation, and then the intrusions looks like the cell network of this SLP, but they are not the conduit for the magmas in the surface floor basalt. Finally, many thanks for your listeners, and many thanks to Tony for his support in Chinese research. Thank you very much.